Hi everybody, Dr. Pringle here. We are going to talk about projections and coordinate systems in ArcGIS. So I've got an ArcGIS Pro session opened here. The first thing I wanted to talk a little bit about is the coordinate systems that you're using. So whenever you open up ArcGIS, you're going to see a base map in here. So we've just got the default one set on here. And it's going to choose a projection for you. And some people don't necessarily appreciate which projections they're seeing as they load this. Down at the bottom, you can see that we've got coordinates that are running down here as we move the mouse. So if we're around Washington, D.C., you can get the coordinates there. If we're kind of hunting around for the point where the equator hits the prime meridian, we'll hit it right around there, just off the coast of western coast of Africa. A few things you notice, though. One is you'll notice Greenland, so this is huge and heavily distorted. And the reason for that is that this is a variant of a Mercator projection. This is actually a web Mercator projection. So if we right-click on this and look at the properties, we can come down into the coordinate system, and we can see that this is actually WGS84 Web Mercator, actually based on a sphere. This is a common projection used for all kinds of web maps. Your base map that we're looking at here is actually distributed as a web map, basically. And for reasons that we'll talk about in lecture, essentially this is a convenient scheme for tiling the world up. And so that's what we're working with. But a lot of the data, the geodata that you're going to work with, is not going to be in that coordinate system. So as an example, I'm just going to Google Natural Earth downloads here. And if you go to Natural Earth, which is a nice little cooperative program between NASAS and a few other organizations here, we'll download some data that we can take a look at. So I'm going to start off by using just the small scale data here. And we're going to download just the country data. And we can unzip it. And then just drag that shapefile in. And we'll get a nice vector representation of the world. When we do that, our base map has disappeared. So we might well ask what happened to that. Part of it has now reappeared, so that helps a little bit. But you'll notice that it changed shape. So the first time that you drag a data layer in, it will essentially start using a projection for that, whatever the first layer's coordinate system is. So what is that? Well, we can right-click on that. We can take a look at it. So that is WGS84. So WGS84 is a world geodetic system. It's got what's called an EPSG code, which is 4326. So this is essentially whenever you're using latitudes and longitudes on a global scale data set or GPS-derived coordinates, you're likely going to be in WGS84. We'll talk about a minor exception to that here a little bit later. Your view coordinates you can actually change. So if we want to look at these in some other thing, we can change those around, and so then you get this is zone 17, and then we've got meters east and north of the origin. But what I want you to key in on here is that the shape has really changed a lot. So Greenland, instead of being sort of this massive structure that looks like this, is still big, but actually the top of it here is getting compressed. So WGS84 essentially just maps these things out as if they're coordinates in algebra class. So 1 degree east, 1 degree north, those are all squares. And when you do that, you get a version that looks something like this. And this is actually quite a bit different than Mercator visually, and we'll just set this back one more time here. and we'll choose WGS84. And in contrast, Greenland here is much larger. Antarctica is massive. You might not notice some of the more subtle changes that are going on in here, but you can really see at the high latitudes the distortion that's happening. So we'll set this back to WGS84. And there it shrinks back again. The next thing that I want to do is to go back to natural Earth, and we had downloaded this at 1 to 110 million. So this is a small map scale. So if you thought of this as 1 divided by 110 million, that number would be very small. In contrast, we're going to use some large map scale data here, and that's going to be at the 1 to 10 million scale. If you divided 1 by 10 million, you'd also get a very small number, but it would be bigger than that number. So we're going to go in here and we're going to download the countries. So we can unzip these, and we'll drag this layer right back on top. So this is the same data, more or less, but the difference between what we just downloaded and what we had looked at earlier is sort of the level of detail that's in here. If we zoom in, we can start to see where these data sets diverge quite clearly. So the green data set was the 1 to 110 million, and it's much coarser, right? There's fewer vertices representing these polygons. Some of these polygons actually don't show up on that data set at all, but it's just a much rougher version of the same data. One of the reasons that you want to be, the version that you're going to want to use is going to be dependent on the map scale that you want to display. So if I'm creating a map of the United States at this, I can actually look down here and see what the scale is that I'm looking at. So this is approximately 1 to 20 million. And what you want to do is search for a data set. If multiple data sets exist, you want to search for the data set that's been prepared for you at or near the map scale that you're using. So if I was making a map of the lower 48 like this, again, 1 to about 20 million, I would probably want to use the 1 to 10 million data set rather than the 1 to 110. And the reason for that is it's just going to look quite a bit better. Now, you may have other reasons. Maybe you want to use this anyway, and you've got a good reason to do that. But if I zoom out and I show something, let's say at this scale, here we're looking at, a 1 to 136 million. So at this scale, I don't want to use the 1 to 1 to 10 million. I want to use this one, the 1 to 110, because this is closer to my number. Of course, you won't find all of these, so you'll have to use your judgment and choose one that's near the scale that you're working with. Why wouldn't I want to just use the 1 to 10 million? The reason is that at this scale, there's so much detail in here, especially along these complicated coastlines, that those coastlines essentially double back on themselves, and you get this kind of smeary border in those areas. It doesn't look too bad right here, where there's not necessarily a lot of detail, but it looks sort of distracting here and there. And so this is a common problem. Rivers make common borders all over the world. And so when those features are complicated, you want to choose wisely which cartographic layers that you're working with. So I want to project my data here. Again, right now I'm working with the so-called WGS84 projection. Now that's not really a projection; it's really a sort of a coordinate reference system. But people colloquially will use that term. They'll also describe this as being unprojected. Both of those are fine. The formal name for this is the plate Carray projection. If we go back to our map and we want to reproject these things, we can basically choose a projection with the data that we're working with. But if we're preparing a cartographic product, then we very likely don't want to do that. And instead, we're going to want to choose a projected coordinate system for visualization that's going to look a little bit more aesthetically pleasing. Now, these have been sort of helpfully broken out according to sizes. Projections will vary according to sort of what kind of shapes. So they might be conic projections, or they might be cylindrical projections. They might also have sort of reference lines or latitudes that sort of center the projection at a certain point or at a certain latitude. And so that's why there's so many of these, right? You can have Albers equal areas, sort of one major branch of projection, or the Lambert Conformal conic, which we'll look at here in a second. But because those have selected latitudes and longitudes that are going to, again, center those, you may want to choose based on where you are. For the moment, I want to use one called a Robinson projection. So Arthur Robinson was a very famous cartographer and developed, among other things, a projection that we call the Robinson projection that looks something like this. It's a fairly nice projection. It's what's called a compromise projection. It's intended to be used for the globe, not intended to be used for any particular location. But if you're taking a global view, then this is nice because it's not an equal area projection and it's not a conformal projection, but it tries to sort of balance all of the different errors that come up into something that looks pretty good. And there are a number of these kinds of projections, these global projections that are quite nice. One of my new favorites is the natural Earth projection. So there's natural Earth and natural Earth 2. That looks a lot like this. And you can see that it's a very sort of pleasing, similar, right? Sort of got this oval shape of the world. And the developers of this have sort of, used the Robinson and many other projections as their inspiration, and then sort of come up with another way of expressing that. I want to show you another, since we're working with projections, I'll show you one other little bit here, and that's if we go back to the small scale data and we look at the physical dimensions here, we can bring in, there's a couple of things that are very nice. Under Graticules, we can download a bounding box. So Graticule is just sort of the expressions of sort of reference of lines of latitudes and longitudes. It'll form a grid if it's a rectilinear projection. It'll look slightly distorted if it's something else. I've downloaded the bounding box for the Earth, and that's going to look like this. And especially as you're working with projections, this is a nice way to sort of take a look at the space. So here's that oval of the extent of the Earth. I'm going to turn off the base layer, so I'm going to move this down below. And we'll just change our colors here to something a little more appealing. All right, that'll be fine. We're suppressing the boundaries for the countries, but that's fine because we're really just talking about projections at the moment. Okay, so the thing that I wanted to show you was the Graticules. I'm going to bring that in here as well. So I'm going to download these at 15-degree increments. We'll save those out. Graticules can be added in ArcGIS, so there's a perfectly fine way of doing that. I do sometimes like to download the ones from Natural Earth and use those instead, because that gives us the capacity to sort of be very deliberate about where we place those. So maybe it's irritating to have them drawn on top of the globe, but if we draw them underneath of our landforms, then it looks a little bit nicer. And of course, this is quite a strong color that's been selected for us here. We could choose something a little more subtle like this. This is not necessarily all that appealing either. Let's try something like that. Okay, so I'm not going to tell you that this is the most cartographically beautiful rendering of this here, but that's not the focus today. We're going to talk about projections. And so now you can see how these lines of latitudes and longitudes, the longitude lines especially, bend out here, and you can sort of pick up a more subtle difference in sort of the spacing between lines of latitude. So I'm going to go back and we're going to just show you again what this looks like for the Mercator projection, which looks something like this. And you can see how the lines of, these are again 15-degree increments, and you can see them spacing out really very widely up here. This is a conformal projection. It's designed to make sure that essentially shape is correct on a local level. But to do that, it bends the space in a very interesting way. These were originally designed for sailing, so you can sort of pick a distant point, and the degree measurement that you would take off of the map itself would be what you wanted to set your compass at and sail to get there. Okay. The other thing that I wanted to look at here was the plate Carray. So this is essentially unprojected, and you can see that sort of unprojecting with respect to the Graticule. You can see that these are evenly spaced. So they're doing very different things. Definitely don't confuse the Mercator projection with an unprojected or a plate Carray or WGS84 projection, because they do look quite different. There are lots of other projections out there. Let's take a look at the Lambert Conformal conic. So this is one that's often used as at the continental scale in the United States. So we will turn off world, and instead we'll look at continental, and we'll look at North America. And this is the North America Lambert Conformal conic. And if we turn that on, we get something that looks like this. This is a very unusual projection for a world map. We would never use it for this. You know, the Antarctica is broken up in very odd ways. We're sort of missing a sector up here. South America definitely looks very strange. But if you zoom in on just North America, that actually looks pretty good. So this is the reason that it's used. It's a continental projection. It's intended to be focused in up here, but it has the sort of detriment that it's you know, gets very weird when you get away from that area. And lots of projections sort of have that property. Let's take a look at another one here. I'm going to turn off these layers, and I'm going to turn on the world topo map. Now, projecting these rasters is actually a fair bit of work, so you'll see these tiling in a little bit more slowly. The UTM projection is intended to be sort of a highly accurate with respect to distance. It's measured in meters, and the way that this works is they set a false origin. They set a false origin, sort of, you know, down at the you know, towards the equator, and then off to the left. And it's intended to be applied in these sort of strips. So these are strips mapped onto the United States, but of course, UTM is a global system. Big divisions between northerly zones and southerly zones. You don't want to mix those up. But essentially, it's a big grid that overlays the whole Earth, and you sort of map things locally that way. So I'm recording this in Blacksburg, Virginia. Blacksburg, Virginia is basically right around here. So we're in zone 17 here. So I'm going to go ahead and project. Actually, first I'm going to zoom in on Blacksburg. Actually, why don't we use Manhattan? This will be a good one. So Manhattan is actually in zone 18. See that it takes quite a bit of time to tile in. Again, it has to project these as we go. If you want to save time, one of the things that you can do is you can pick a layer that essentially corresponds to the layer that you're using. The base map layer here is coming in Web Mercator. So you'll notice that the map is much more responsive as I move around when I'm in that projection. It doesn't have to do all this work of sort of bending the geometry. So we'll leave it here for now. The block system in Manhattan looks something like this. It's quite rectilinear. Maybe we want to choose something a little bit more boring. We could choose Chicago as an example of a road network that's mostly oriented north-south. There's actually some very interesting errors associated with their grid system that makes it not quite north-south. So that's maybe out. Washington, D.C. ought to work pretty well. Washington, D.C.'s street pattern is actually fairly strange, but it is laid out according to sort of regularly sized units, so I think that this will probably work well all these little avenues connecting to different parts of the city are a neat feature of Washington, D.C. Okay, so we want to project this. I'm going to right-click here and do Properties, and this time I'm going to choose a projection that's going to be a UTM projection. Now, one of the things that you'll notice here that there are a lot of variants. These are divided up also by region. There are a lot of variants of these, unfortunately. But the two that you're most likely to run into are WGS84, which is, again, mainly divided in northern and southern hemispheres. We'll have to check real quick to make sure that we're going to be in the right spot. DC is around here, so we're going to be in zone 18. So if we pick 18 and hit OK, it's going to reproject that. The other version of this that you're really likely to run into is the North American datum of 1983. So WGS84 and then NAD83 right here. NAD83 similarly has UTM zones. Now these are different, and so it is important that you're going to sort of choose the one that's related to what you want to do. Visually, the differences are likely to be indistinguishable, but they are different coordinate systems. A lot of the data that gets distributed in the United States is distributed as a NAD83 base layer. Certainly ARC can handle the reprojection from one of these to another. But if your data comes in, let's say it's data that's sourced in the United States and it's prepared by a United States agency like the USGS or distributed on the national map, then probably that stuff is going to come to you in the NAD83 coordinate system. So you're probably better off projecting it this way, just to save kind of computation time. However, this data here is distributed as WGS84 data, and so you wouldn't necessarily want to use NAD83 for this, unless you had a particular reason to do so with the map that you were making, and you may very well, right? If you're producing maps for a United States government organization, there's a good reason to use the NAD83 coordinate system, even on output. Okay, so I projected this into UTM 18. If I zoom out, I'm going to actually turn these base layers off, and we're going to go back to just using our layers here. So one of the things that you'll notice is that the Earth looks a lot stranger. So here we're adding in our bounding box here. We're missing huge chunks of this. UTM is very much not a global system, so it's only going to stay intact sort of within this narrow band based on its sort of central meridian. And the more you get away from that, the more things are going to get wrong. And you get so wrong, essentially, as you get outside of this, that ARC is basically not bothering to do the reprojection. So it's really intended to be a local coordinate system. And then the other really common one that you'll run into is state plane coordinate system. So let's jump in here. All right. So these again are the major classes. We're in projected coordinate system. We come into state plane, and again, there's a lot of sort of detail in here. We're not going to talk too much about these, but the common one that you'll find in the United States is NAD83 2011, and even within that, you can sort of choose whether you're using international feet or meters or U.S. feet. It does get fairly confusing. You may have good reasons to choose between these, but most of the time, for the things that we'll prepare, it'll be in meters. You may have a client that's not true for, and so you may very well want to use feet instead. But we're going to go ahead and use this, and we're in Virginia. So I'm going to choose Virginia. Virginia has two. We've got a north and a south, and Blacksburg is in the south part. So we'll hit OK. It's going to reproject this data. And again, the state plane system is really only intended to work locally. You know, the mathematics of what you see outside of that still work, but it's a very distorted system globally and not intended for that use at all. We're going to zoom in here. I'm going to turn this back on, turn this back off, and what I want to see is zoom in. Again, a lot of work to do this reprojection at this level. Your computer is sort of working really hard to turn this into what you're asking it to do. Let's see here. So there's Lynchburg. So Blacksburg is roundabouts here. Ooh. All right. So I'm just going to reproject this back while we're hunting around. There we go. So when you're local like this, the projection works quite well. This is a good projection to use if I were making a map of Blacksburg. This is a bad or if I was making a map of Southern Virginia. It's a very bad projection to choose if I'm using some kind of a regional model. So there's a quick introduction to sort of the practical parts of projections and coordinate systems. This stuff takes a while to get the hang of. So if you don't quite understand everything at the end of this video, that's okay. But I hope that you understand sort of the differences between sort of world-scale projections like the Robinson projection or the Mercator projection, and continental kinds of projections such as the Lambert Conformal conic, and then projections that are really intended to operate at the local level like UTM or state plane. All right, thanks everybody. We'll see you next time.